Hi, Mads Barnkop from Kaiser Power Electronics here. Today we're taking a look at the circuit analysis of the Nokia Siemens Networks FXEB, which is a 3 times 80 watt 1.8 gigahertz power amplifier for cell phone base stations, and this is the actual board we are talking about. So, as you can see here behind me, we have the functional block diagram for this amplifier, which I found available in a large brochure for the whole series of this Multiradio BTS system. So first, we will just take a brief short walkthrough of the circuit diagram. Then I will move on to show the duplexer, what makes the difference between the transmit and receiving part, and then we will move on to look at the RF control part, which consists of the FPGAs, the network interface, and so on. Next comes the transmit and receive parts, where we have all the analog to digital conversion and all the digital to analog conversion, where on this side of the board we have both the transmit and receive parts. And we will move on to look closely at the circuit signal path for the receiving main part and also the transmit main part, and we will move on to also look at the receive diversity amplifier. And last but certainly not least, we have the power amplifier boards. These are really the heart of this unit. This is where we see some really neat RF design details, so I'm really looking forward to that part. And I will round off with the power supply, which also has a few different quirks from what I have seen before, and we'll dive into those details. So let's get started. Throughout the circuit analysis, the big yellow cursor will help us see what's going on. If we take the duplex filter first, there is this RX port. It will be named 5, and then we have the TX and RX port up here, which I will mark 6 when we look at the picture of the duplex filter itself. Now inside the duplex filter we have a few small PCBs with a few components on, and these make up the VSWR, which is the voltage standing wave ratio measurement, which is a measurement of the reflected energy from the impedance mismatch between the amplifier and the antenna, and this is a measure of how efficient your amplifier is working, since there is no such thing as an amplifier that is matched 100% against the load. Behind that we have the bias T, and this is where the DC is filtered out from the RF signal. And then we have the TX and RX filter itself. The LNA, which is a low noise amplifier, is not really present inside the duplex filter, despite being inside the dotted line here. From the functional overview, we could remember that I said we have marked 5 for the receive port and 6 for a combined transmit and receive port, which are the antenna connectors here at the front of the amplifier, or the duplex filter. Now the receive channel only had a bias T, which is what we can see, the small weirdly shaped PCB sitting down here in the corner. And over in the TX RX part we have another PCB which contains both the VSWR measurement along with the bias T. So let's take a closer look at these 3 identical cavities for each amplifier. So let's just zoom in here. Now, as we can see here, the receive channel is a completely separate channel which has no connection to the transmit filter, and it also has very few couplings. As we can see, there is actually only this tiny bridge here which is used to shape the received signal. I have put a link into the description of this video to another video I did where I explain how duplex filters work and how these cavities, why they're shaped like they are, how couplings work, and so on. So check that out if you're really interested in that topic. Now if we look at the transmit and receive part channel over here at the receive and transmit 6, we can see that the transmit part usually have larger resonators due to the higher transmitting power compared to the receiving power. But we can also easily recognize a transmit duplex filter by the amount of couplings that we see here, which is a isolated piece of conductive material that sits between two cavity chambers. And as we can see here, there are more cross couplings and even more, a small one here, and we have a double connection to the output up here. Now if we first take a look at how this board is set up, we have a RF section sitting here at the top. There is a processor sitting here, one for each channel or amplifier. We have this Nokia Siemens Networks CPU sitting here, which is codenamed marked Murku 2, which I assume is a Finnish codename from the Finnish company Nokia. And we have a FPGA sitting here, and looking at the data lines and the abundance of a dedicated network controller, I'm guessing that this FPGA handles the network traffic handling between the three amplifier CPUs sitting up there. To control the whole amplifier itself, there is both the Murku 2 and also a Freescale PowerQuick 2 Pro CPU. This has some peripheral features built in, like a network controller and such, and also has 2 times for 512 MB of DDR2 SD RAM. So let's jump into a zoomed in look and look on a few details around the CPUs. Now down here at the optical network interfaces, we also have a lot of power supply going downwards on the board and all around the edges here. Here we have the main CPU, which handles most of the network traffic and housekeeping job of the amplifier, ensuring all measurements are collected correctly and sent back onto the network and so on. And this is what I suspect to handle the network interface up to the these single channel FPGA CPUs. But it is for sure that I have seen these CPUs before in other amplifiers, and this is where we generally would see the decoding of the telecom packets protocol into the single bit stream data that is handled by the digital to analog converters along with the CPU. Moving on to the analog signal processing, first we are taking a look at the RX Diversity low noise amplifier that we saw inside the dotted line for the duplexer. Then I will move on to the RX main and the TX RX signal processing. Here they are mentioned as 2 separate boxes, but on the PCB itself it is hard to make out which is really which, so we'll just take that as it comes. Here at the grand overview, at the top we have the RX Diversity, then we have the analog to digital section here, which would be the receiving part. And over here we have the DAC, which is the digital to analog conversion, so this is our transmitting part. We also have our PLL clock sitting here in the middle, and over here is a lot of discretes which is used for a analog to digital conversion that sits on the back side, so here we will switch to another picture. So let's first zoom in on the low noise amplifier and take a look at that. Here we have the input from the duplexer, which goes directly into an NXP low noise amplifier, which has a very narrow working frequency bandwidth. From here we can see the big power supply rails sitting at top here. The signal exiting here goes through a Anarin Singer 1P50 or 1P503S, which is a 3 dB hybrid coupler. Here we can see the phase change through the coupler. One goes down through a, I think that's a ceramic filter, but I'm not quite sure, and down through a grounded line. Then there's two smaller amplifiers sitting in a cascade here, before it goes into a ceramic resonator bandpass filter. One of the receive lines begins its journey over here, where we have the connection to the duplexer. There is a lot of impedance matching along the signal line, which goes up here, ends through a mixer or IF amplifier, where the signal is sampled down to a lower frequency signal. I also did a detailed view on in another video on that, so check out the description for that topic. Here we can see the dual lines exiting out of this before entering into the analog devices 89255, which is a 14-bit ADC, which has a single line out for 125 megasamples per second. Now this feeds a single bit stream down to the CPU, which encodes it back into the telecom protocol and sends it out on the optical fiber network. The signal resolution on the transmit part is however much higher, as we can see here on this analog devices 89122, which is a 16-bit DAC. It has a whopping 1230 megasamples per second conversion on dual lines. So we can see a lot of data points for the digital input connecting down here at the bottom, and we have the two dual line outputs, as we can see, impedance matching, some small filtering really goes up here, and we have a small maybe a low noise amplifier. It does not have any part codes that I could read out even under my microscope. Then up here we have a ceramic resonator bandpass filter. I did a detailed thing on ceramic resonator bandpass filters in another video. There's also a link to that in the description. Now I did mention that this was the heart of the amplifier. This is the PLL, which is a up to 6 GHz clock generating circuit. So all we do here is generate a very high speed clock, which is used as the intermediate frequency in the down and up conversion mixers that I also showed earlier on the first receive part with the ADC. I also did another video where I looked detailed into down and up conversion, so if you like that topic, check out the description. Now here we have a ADL 5356 dual mixer or intermediate frequency amplifier. Here we get this is actually the output end of this, so let's go down to the start of this. Down here we have the first amplifier, which comes from the ADC on the other side that we will check out afterwards. But here we have a variable gain amplifier. As we can see, it has dual input lines, and it has sonic acoustic wave filters sitting along the line before we get into the digital attenuators. So here we can digitally adjust the signal strength to suit the impedance of the amplifier, or actually just adjust the signal to the load on the amplifier as to lower the reflected energy back from the antenna. About the sonic acoustic wave filters, I also did a detailed video on that, so there will also be a link to that video in the description. So up here we have at the end the intermediate frequency amplifier, and this is the last step before handing this signal over to the power amplifier. So let's take a look at the ADC itself. This ADC had its own little shielded housing on the back side of the board. So let's dive in. It doesn't really contain that much. There's a few switches or power supply, but else all the data lines and so on is all routed down through the layers of the board. So all we can really see here is that we have a analog devices 14-bit ADC with 2 times 155 megasamples per second bandwidth, and this is what is fed from or is feeding data from the converted analog signal and back into the protocol conversion CPUs. The power amplifier, finally. Now, just at this day of recording, I received an email from a radio amateur and electronics expert, we can call him, that did reverse engineer this particular amplifier that I sent him. And he found out some very interesting details about how simple you can actually control these amplifier boards outside of their native environment. So let's dive into that. First, you can see here a overview of the 1/3 of the amplifiers, and it also has 3 LDMOS output transistors. But let's get down and start at the start. So down here in the right corner we can see the input pins for the 28 volt and the ground, and it also has a pin marked power amplifier enable. And what he found out was that just connecting power to this amplifier and pulling PA enable high with 3.3 volts, the amplifier actually got active and started amplifying the signal that you put into from the input. Now he also reverse engineered that this is actually a digital potentiometer, which is a analog devices I2C component, along with a LM75A digital temperature gauge, which is also controlled by a I2C bus. And he wrote a Arduino library to control these two ICs, so you could control the amplifier without the native environment. Very cool stuff, and I will ask him to post his results on the High Voltage forum in this post for this video, so you can all see the results if you're interested in those as well. Now, if we follow the signal path down here from the 2 golden connectors, it first enters the first NXP amplifier here, which is a pre-amplifier of just shy 40 watts. As we can see, it has really heavy power supply decoupling sitting around the corners. From here on we still have a single signal line going up here, going through the first signal split up here, where we have a 2 Anoran Singer 3 couplers. First we have a 5 dP coupler and a 3 dP coupler. And this is where the signal gets split out into the 3 lanes with the output transistors. And this is where we can see the phase shift over here, and the other one 90 degrees out of phase and a 50 ohm termination. And the same up here, again a 90 degree phase split through the coupler up to the output transistors, which are Amplion LDMOSs. Another point he mentioned due to the temperature gauge is that LDMOS is really temperature dependent when you have to control their gain, so that is most likely to adjust the input according to the temperature of the module. But as we can see here, each output transistor has again a lot of decoupling, heavy traces, and we will see a lot of long signal path, so we ensure there's probably the quarter or half wavelength signal path on the power supply rails to avoid any noise injection, which we can also see out here in the corners. So if we move up towards the output again, where we see the recombining of the 3 output transistors, as we can see here. There's really no indication that this should be a Dorothy amplifier setup. I think this is more working in a interleaved way, that each of these transistors are not transmitting or have the little baby smiley sitting up here in the corner. Oh, grounded baby. And last but not least, we have the output circulator, which is where we ensure that any signal that we put into port 1 is only outputted at port 2 out to the duplexer. So any energy reflected back from the antenna mismatch, which comes back from port 2, can only circulate over to 3, where we have a 50 ohm power resistor termination. So any reflected energy from the antenna is dissipated as heat down here in the power amplifier module itself. The power supply is split into 4 sections, or actually 5 sections. We have a input section where we have the 48 volt telecom standard input. We have these 3-legged TVS, which we will look at, or varistors, which we will look at last. But also it's split up into 3 power supplies here, one for each amplifier module, which consists of a planar transformer, a choke, and it has its MOSFETs sitting on the back side. Then over here we have another planar transformer and output choke for the what we call it, control logics power supply. And if we take a look at the back side here, again we can see the input side over here, and we have a lot of ceramic decoupling here on the back side, along with the dual MOSFETs and a single output diode for each of the power amplifier sections here. We can also see the connection points to the power amplifiers down here at the bottom. Now a few details about the power supply is that up here. I'm sorry for the little blurred image here, but there's actually these gold-plated small components here are fuses, and having 10 of those in parallel, 5 per rail, is actually how this unit is fused on the input side. And the last thing for you to enjoy is here the 3-legged varistor, trademark of Nokia Siemens networks. And yeah, I don't know what the purpose of that is, but as you can see, they have just soldered on a 3rd leg onto a off-the-shelf varistor. So I really hope you enjoyed the circuit analysis. I hope you will watch some of my other videos where I cover a lot of the topics in this video in more details. So yeah, until next time, see ya.